Welcome to Astronomy Daily, your regular update on everything happening in the cosmos. I'm Anna.
And I'm Avery. We've got a jam-packed episode today, starting with some big news from SpaceX.
Very big indeed, and the whole Starship team and SpaceX in general need to be congratulated.
That's right, Anna. SpaceX today made headlines with its highly successful suborbital mission of the final version 2 Starship Super Heavy rocket. This incredible flight involved crucial testing of its heat shield and a simulated deorbit burn, marking a significant step forward.
Indeed, Avery. This suborbital flight of the final version 2 Starship Super Heavy was a resounding success. The heat shield test was flawless, and the simulated deorbit burn performed exactly as planned. This incredible achievement paves the way for SpaceX to now move to version 3 for orbital missions, which is absolutely critical for programs like NASA's Artemis. A key technological hurdle for those ambitious missions will be in-orbit propellant transfer, and this success brings that closer to reality.
It's truly a testament to SpaceX's audacious approach to rocket development. This highly successful flight unequivocally validates their iterative test, learn, and iterate philosophy. Unlike traditional aerospace programs that might spend years on ground testing, SpaceX gathers invaluable data from each flight, rapidly advancing the Starship program. The Starship system is designed to be fully reusable, a game changer for reducing launch costs and enabling large-scale missions to the Moon and Mars. The sheer scale of Starship, being the largest and most powerful rocket ever built, presents unprecedented engineering challenges. And this successful suborbital test is a crucial step in pushing the boundaries of what's possible in space transportation towards orbital missions.
The sheer scale of Starship, being the largest and most powerful rocket ever built, truly cannot be overstated. When fully stacked, it stands nearly 400 feet tall, dwarfing even the Saturn V rockets of the Apollo era. This immense capacity is what makes it so revolutionary. It's not just about reaching orbit, it's about delivering massive payloads, hundreds of tons, to the Moon and Mars, and eventually transporting hundreds of people. This successful suborbital mission is a monumental step, demonstrating critical capabilities that pave the way for a future where space travel is routine and ambitious multiplanetary missions become a reality, especially with version 3 now on the horizon for orbital flights. Moving on to other spacefaring nations, China successfully launched a Long March 2D rocket, carrying the Haiyang 3 satellite into orbit. This mission marks another advancement in China's growing space capabilities, particularly in Earth observation.
The Haiyang 3 satellite is designed for marine environmental monitoring, which is incredibly important for understanding our oceans, climate, and coastal regions. These satellites provide vital data for everything from disaster prediction to resource management. It's a testament to the continued global investment in space-based observation systems.
Indeed, Avery. These Haiyang satellites are crucial for global climate science. They provide continuous, high-resolution data on sea surface temperature, ocean color, sea ice distribution, and ocean dynamics. This information is vital not only for understanding changes in our planet's climate and its impacts on marine ecosystems, but also for practical applications, such as monitoring marine pollution, supporting sustainable fisheries, and aiding in maritime disaster response, including tracking oil spills and predicting harmful algal blooms. China's investment in this satellite series demonstrates a clear commitment to expanding its capabilities in Earth observation, positioning itself as a key player in international efforts to monitor and protect our planet.
Now, for something a little more celestial and less man-made, the Northern Taurus meteor shower is now gracing our skies, peaking around November 12th. Known for its bright fireballs, the Taurids are sometimes referred to as the Halloween fireballs due to their early November appearance.
They certainly are a spectacle, Avery. The Taurids originate from debris left behind by Comet 2P Encke. What makes them unique is that we pass through two streams of debris each year, the southern torrids in late October and the northern torrids in early November. This year, experts were predicting a potentially stronger showing with more bright meteors than usual as Jupiter's gravity has perturbed the stream, bringing denser pockets of debris closer to Earth's orbit.
Comet 2P Encke is a fascinating object, a short-period comet that completes an orbit around the Sun in just 3.3 years. This relatively frequent passage near the Sun means it sheds a considerable amount of dust and debris, creating the two distinct streams that give us the northern and southern torrids. What's particularly interesting is how Jupiter's immense gravitational pull can periodically sculpt and concentrate these debris streams, leading to years like this one, where we might experience a higher frequency of brighter meteors or fireballs. These fireballs are essentially larger dust grains or small pebbles from the comet that burn up intensely as they enter Earth's atmosphere, creating a dazzling display. For stargazers, clear, dark skies away from city lights are always key, but understanding the radiant point in the constellation Taurus and checking for moon phase can also enhance the view and experience. It's a beautiful reminder of the cosmic dust our planet constantly sweeps up as it journeys through space.
Shifting our gaze back to historical space exploration, NASA has opened pristine lunar samples from the Apollo 17 mission, which returned to Earth in 1972. These samples have been meticulously preserved in a vacuum seal for over 50 years, and scientists are now studying them with modern analytical techniques.
This is a truly exciting development. These untouched samples offer an unparalleled opportunity to study the moon's geology without any terrestrial contamination. Scientists are hoping to gain new insights into the moon's formation, volcanic history, and the presence of volatile compounds, which could be crucial for future lunar missions and understanding the origins of water on the moon.
Scientists are particularly interested in the volatile compounds preserved within these vacuum-sealed samples. Volatiles like water ice, trapped gases, and organic molecules can provide critical clues about the early solar system, including how water might have been delivered to both the moon and Earth. The advanced analytical techniques available today, far more sophisticated than those of the Apollo era, allow for incredibly precise measurements of isotopic ratios and chemical compositions. This can help differentiate between different sources of lunar water, for example, distinguishing between cometary impacts and solar wind implantation. Furthermore, understanding the distribution and characteristics of these volatiles is paramount for future lunar habitats and resource utilization. If we can reliably extract water and other essential compounds from lunar soil, it dramatically reduces the cost and complexity of long-duration missions, enabling a sustained human presence on the moon and supporting deeper space exploration. And finally, as space exploration continues to accelerate, the issue of low Earth orbit, or LEO congestion, is becoming increasingly critical. A recent study highlights the urgent need for international cooperation and sustainable practices to manage the ever-growing number of satellites and debris in orbit.
The study, conducted by a consortium of international space agencies and research institutions, underscores the escalating risk of collisions in LEO. With thousands of active satellites and an ever-increasing amount of space debris, the potential for catastrophic cascade events, known as the Kessler syndrome, is a serious concern. Such events could render certain orbital altitudes unusable for decades, impacting vital services like GPS, weather forecasting, and global communication. The Kessler syndrome is a particularly grim scenario, where a single collision could trigger a chain reaction, creating so much debris that LEO becomes a perilous junkyard. Imagine losing access to satellite navigation, accurate weather predictions, and the very internet connectivity that powers our modern world. It's not just about losing a few satellites. It's about jeopardizing the foundational infrastructure of our global society. This isn't a distant problem. The risks are increasing with every new satellite launch and every piece of debris generated. Urgent, proactive measures are needed to prevent this cascading effect and preserve LEO as a vital resource for humanity. Addressing this critical issue requires a comprehensive, multifaceted approach, encompassing stricter regulations on satellite launches, a universally adopted code of conduct for space operations, and significantly improved tracking of space debris, even down to centimeter-sized fragments. Furthermore, the development and deployment of active debris removal technologies, which are still in their nascent stages, are becoming increasingly vital. International collaboration is not merely beneficial, it is absolutely paramount. Space is a shared global resource, and the actions of any one nation or commercial entity can have far-reaching consequences for all. Organizations like the United Nations Committee on the Peaceful Uses of Outer Space are actively working on establishing guidelines and best practices, but a more rapid implementation and robust enforcement mechanism across all spacefaring entities are urgently needed. Without concerted global effort, we risk creating a future where low Earth orbit becomes too hazardous, if not entirely unusable for essential space operations that underpin much of our modern infrastructure and scientific advancement.
The urgency of this situation cannot be overstated. Beyond the risk of direct collisions, there are concerns about light pollution from large satellite constellations interfering with astronomical observations, and even the potential for military implications if certain orbits become weaponized. Effective governance of outer space must evolve rapidly to keep pace with technological advancements. This includes developing clear legal frameworks for liability in the event of collisions, promoting data sharing on satellite positions and trajectories, and incentivizing private companies to adopt sustainable practices, such as designing satellites for deorbiting at the end of their operational life. Without these collective efforts, the dream of a vibrant, accessible space economy could quickly turn into a nightmare of orbital debris, limiting humanity's reach beyond Earth for generations.
The implications of unchecked LEO congestion are truly profound. Beyond the direct loss of satellite functionality, there is the long-term environmental impact. Each collision creates thousands of new pieces of debris, exacerbating the problem and making future launches even riskier. This isn't just an inconvenience, it's a threat to our continued access to space, which has become indispensable for modern life, affecting everything from global commerce to disaster response.
That's all for today's Astronomy Daily. We've covered a lot of ground, from the ambitious endeavors of SpaceX and their monumental Starship tests to China's significant advancements in Earth observation with the Haiyang 3 satellite. We also delved into the dazzling spectacle of the Northern Taurid meteor shower, the invaluable scientific treasures unearthed from Apollo 17 lunar samples, and the critical, ongoing need for managing low Earth orbit congestion for the sustainability of our future in space. It's clear that the universe and our interaction with it continues to present both incredible opportunities and significant challenges, reminding us of the constant push for discovery and responsibility. Join us again tomorrow for more updates from the cosmos. Until then, keep looking up.